example, well, I not only get Twitter.com, but I also get information on which user profiles the link has been most often clicked. But so this might be actually very interesting because we can formalize this clickstream directing capacity not only in terms of graph theory, that so many retweets, but actually looking at how and compare. That if two people post the same link, well, you can see more people have clicked it on their profile than on theirs. But, and there's a big but, because I'm mostly interested in the big buts, time is really bad in there. In a sense, we have an update cycle of our 10,000 accounts. We basically download them two times a day because Twitter doesn't whitelist research projects. They whitelist mashups, but they don't whitelist research projects. And of course, the time that between the post of a link and the time we're getting there is very different in different cases. So, of course, we have this bit.ly measure, but we have it at a point in time that is not equal concerning our research sample. So that's I think a very important point that this time notion is not only a conceptual notion, but already just downloading a snapshot from the web is never downloading a snapshot from the web. Meaning you cannot just ask all your if you do link analysis, you cannot just query all your links at the same time, or you don't have a lot. You always have a temporal element in there, and in our case, that temporal element may be quite important because Twitter is so fast. We've been working on a couple of visualization tools that allow us to see retweets, and it's extremely fast. So if we, for example, crawl a link, a certain account, half an hour later than another account, well, there goes our scientific work. Okay. Fourth problem that we've encountered is sampling. And Twitter actually is a tool that you can sample quite easily if you're interested in the whole of Twitter. Twitter has, like Facebook, for example, they have continuous account names, meaning you have the first account, the ID is 1, and then you have the last account, and if you open an account now, you will have the highest number. So you could basically just take the highest number, say, well, we want to have a sample of 10K, and then just extract 10K numbers from there by random methods, and that will work. But our project is targeting a specific language space, not necessarily only language space, but a particular media space that is actually sometimes multilingual. It's difficult to localize only using geographical measures. So what we're doing is, in a sense, localized full sampling. But what are we doing? Where do we stop? What is our stop measure? And if you look at, this was just a test sample that we've been working with in the beginning to just start building the tools. Here we have the network. Where basically it was a test sample of 400 accounts. We looked at who's linking to who, and the people on the center, of course, are the most linked to. And you have the size of the bubble is how many friends they have, and the color of the bubble is how many people. No, sorry, it's the other way around. It's the size is how many followers they have, and the color is how many people they follow. So you have, for example, up there, always using that example, you have it's NKN. She's a French politician. She's very, very, very followed, but very few people follow. We can say, okay, this might be a network as such, but if we introduce another measure in here, namely the number of tweets posted by those accounts, what we instantly find is that in here that the size of the bubbles is the number of tweets over a given time frame that actually it's not necessarily people in the center that post the most. And well, this might be this might actually only be astounding if you're as naive as I. But what this graph made us see is that, well, every network sample that we take is surrounded by other networks. Meaning there's only on Twitter there's only one network. So our stop measure is necessarily completely artificial. Because even working, for example, with language trees works very, very badly. So sampling by network density, I think it is interesting, but there's a series of questions. 5, last point of the series of questions. How smooth is a curve? That's a small visualization library program. It has a parameter for each curve, its smoothness. Right? So you see, for example, the black curve says higher smoothness than the red curve. The result is that, for example, here you get the nice full body. But of course, nowhere in time, at no point does the data express anything here. Yeah? So the highest point is here. So we always have a series of trade-offs to make between a beautiful representation and an accurate presentation. And even accuracy can really be discussed. I just want to show one tool we've been working on. Yeah, it's very interesting. People love the Anilka. That's basically one of the tools. I think what we're trying to do in that project is build tools that can be used by researchers when it's tools that are built for that research project. Okay, but we have a series of researchers who do qualitative research, and we want them to be able to use the tools we built to do their research. So we have an interface where you can do a series of things. And here, for example, that's a stacked graph where you basically have the possibility of seeing, the absolute number of tweets for the 3 terms I just entered, and also, well, you have the relative relation between them by just comparing the height between them. For example, here you have for the word flotilla, you have 707 tweets, and here Sarkozy, which is kind of the baseline. It literally is. It literally is. He's always there. 313. Yeah? This is Anelka. Yeah? It's the guy, the football player that insulted his trainer. And so here, in a sense, well, the question of accuracy really starts here, because here the volume of our data, the body, is directly related to the message that we are trying to transport. And here there's a big question between smoothness, for example. And is it should we just use straight lines, which we did, or should we use it? Here. So what kind of problems are these? Are these technical problems waiting to be solved? I think also, already, yeah, those problems never come alone in a sense. Very often you have the let's say a problem concerning time is connected to a problem concerning computing resources. For example, if we had bigger cables, if we had a bigger computer, we could sample perhaps more often, and that way we could better treat the topic of time. Yeah? So there's a series of questions that are clusters of questions, perhaps. Yeah? And well, my second point here is to say that, well, the solutions that we're going to find are in fact not solutions; they're decisions. They're decisions that are not only decisions that fall from the sky. They're grounded decisions in the kind of what we know, what we can do, the resources we have, etc. So if you look very quickly on this graph, I would like to argue that I don't know if you can read that, it's a little pixelated. On the downside here, I try to express concreteness, on the upside, abstractness. And in a sense, I think in a lot of the projects we're building, where we're going from a phenomenon that we're already seeing in a certain light, of course. We're doing some initial modeling, data selection. We're slowly going into the formal space. Here we're not formal, we're just starting to look around, what am I interested in. Then we do data patching, filling up holes, data transformation. For example, if we would clean our localized database, if you would say, okay, I'm not happy with the way location is represented, I go there and either I automatically clean it up or I manually clean it up. Then we do, of course, apply analytical models. We do data fitting in the literal, in the classical sense of, for example, fitting a curve to a data cloud by using least squares, for example. But I think we're doing research fitting all the way in a sense. We're always going back in a sense to the concrete, even when we're in the formal. Representation, visualization, building an explanatory model, and in the end we have a scientific narrative. That is something that is of course not very formal. I mean, there are formal aspects in there, but still there's an article, there's language, there's a presentation of our research. So in a sense we're going from a non-formal space through the formal arc back to something that is at least in part informal again. The interesting thing I think about this is that what I would like to call epistemological drift, meaning that this very neat graph actually is mobile, permanently mobile, meaning that the moment we're looking at the phenomenon, we're already coming with a certain series of preconceptions. So, for example, if our preconception is I want to study stuff by using different visual methods, that phenomenon is not going to be the same phenomenon as if I say, my background is I do questionnaires. Yeah? So we have actually the formal already in here. And every time we're in the formal, we're also, of course, and this is why I use those many examples, is those are technical problems inside of modeling, but we always consciously are not feeding them back to what we think might be plausible. So I cannot build a research tool on Twitter without actually a preconceived idea of how Twitter works, what it is, etc. And that's going to be it's going to play a role all the way. So I'd rather use the mist of formalization and postulate that there's a zone of that we move in where we have of course we're not blind in the forest running against trees, but we have to make a compromise and decisions. How much time? Oh, just one last point. Sorry that I was a little long. Just one last point then. I want to refer you to a paper by Lauren Daston and Peter Gallison, the image of objectivity, which I find really interesting for the question of digital methods. That paper is not so much about the use of images over the time. For their argument is basically images have been used in science, in scientific communication for a very, very long time. And what they analyze are physiological atlases, so basically displays of the human body in the several stages of decomposition. So they say, well, basically we always had images for a very long time. It's also not so much what is changing for them the use of those images. Those images were used to transport knowledge, also to have a certain persuading power. What they say is what really changed is what counts as a good image. And this is an example from 1749, where you can instantly see, the skeleton. You will never see a skeleton like this in real life. It strikes a pose. It is idealized in many forms. And the goal for the creator of